Good evening and welcome to the inaugural lecture of Professor Ruth Misener. Inaugural lectures are a celebration of the individual achievement of an outstanding academic, but I think they also are a celebration of a great department of computing and also of Imperial College and its mission. This lecture, I am sure, will exemplify how we can meet this mission, because I can't hardly think of anyone who epitomizes this kind of DNA of Imperial by combining very foundational research, mathematically grounded research, with the need and the desire to transfer this into impactful applications, and also to reach out to industry and have engagement with them, and even do executive education on top of this. So I think this is really an event that I look forward to very much. But before we do that, I need to get some housekeeping out of the way. This is an online event as well, so I would like to welcome the online audience here. In the event of an emergency, the fire exits, you can see here the two green exit signs, so please follow those and also follow the directions of fire wardens. The assembly point is on the corner of Queensgate and Prince Consort Road. I should also say that the event will be recorded. A Q&A will take place after Professor Misener's lecture. If you have questions in the audience, please wait for a handheld microphone to be brought to you before you raise your question. The online audience also has an opportunity to ask questions, and that will be facilitated in the online channel. So without further ado, I welcome Professor Ruth Misener for delivering her inaugural lecture. Thank you.
Thank you very much. So thank you so much, Michael, for that very, very kind introduction. Delighted to see everybody here. Thank you for coming, especially when there's been this annoyance with Wednesday and now Monday and blah, 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 blah. So really, really appreciate everybody making the effort. Okay, so the title of my talk is Just Relax. And the first and sort of most important thing to say is I'm completely delighted to get to give a lecture like this in front of such an amazing set of colleagues. And the reason that I'm able to give such a lecture is that I've gotten to work with a collection of very outstanding people over the last years. So these are the PhD students, the postdocs, and the research fellows that I've worked with the last 8 years in Department of Computing. And this is ultimately sort of a reflection of how amazing they have been. And I also wanted to mention maybe all the people I've written papers with here at Imperial, people who were employed here at the same time I was, and I didn't have a supervisory role, but I did sort of collaborate on a paper with them. I haven't included everybody where we collaborated on grants, or we collaborated on teaching, or collaborated on all sorts of other things, mostly just because the slide would explode. And then the last couple people to mention before beginning, many of you won't know this, but my PhD supervisor, Chris Flutis, extraordinary guy, he died very young at the age of 56 in 2016. When I do it correctly, I remember to put the people first, and then the things that we do here in the university, the research and the teaching second. And he's the one who taught me that. Ever since he died, my postdoctoral supervisor, who will give the vote of thanks at the end, this is Stratos Pistokopoulos, has basically had to do double duty also as my PhD supervisor. Okay, so diving into the technical details, what is it that I want to do? Well, I want to get the best answer possible. I'm in computational optimization, so I want to solve a mathematical problem that tells me how to get the best answer possible. First, why do I want to do this? Well, let's be really straightforward. I'm really competitive. In this audience, I might not even be in the top half, but I'm reasonably competitive. So I would like to do the best possible. If I was going to be giving the same answer to, or my justification to an industrial audience, I might say, well, I might like to know when you just stop bother improving or something like this. Another thing, and this will turn up in research where, say, you're interested in maybe a thermodynamic equilibrium or some sort of concept in
chemical engineering or biomedical engineering, is that nature may end up finding the minimum of some sort of function. You make your decisions, and then nature finds the minimum. And so if I end up finding a solution that's not quite as good as the minimum, well, that might be a bit of a problem, because basically nature is going to find the actual best solution. So I would like to with my algorithms. So how are we going to do this? Well, in the case of minimization, the trick is to just relax. So what you do is that you just imagine the most comfy, cozy armchair that's absolutely perfect. And basically, the global minimum is at the exact same point as where sort of you're the most comfortable, at the lowest bit. This is an optimization problem that I've set up with special properties. But when you have these special properties satisfied, the relaxation, you can solve a very easy problem at that point and get the global minimum. OK, so all I've been doing here at Imperial is basically figuring out how to relax better. So let's look at why it's actually challenging to be able to relax and why I can think about this as research. I'm going to take this optimization problem, and I only have 2 input variables so that I can make this quite simple, x1 and x2, and I want to go down as much as possible. So basically, I want my x1 to be as small as possible, my x2 to be as big as possible, and then I want to obey the constraints. And so you can see where the answer is. And now what I'm going to do is I'm going to look from on top. So we're going to see only the contours of the feasible space so that I can show you what the challenge is. OK, so the rules are I have to stay below this red line, to the right of this red line, to the left of this red line, and above this red line. So that's the feasible region, right? And the issue is, for sort of a local optimization algorithm, would be that I might have a point that I think is really, really good, where if I'm going to be looking in that sort of local space, I say I can't get any better than this. But that might not be the best solution. This was the downhill bit that was the best. For this particular optimization problem, to be able to solve it, one thing that I could do is I could just take this relaxation. And what's going on is that this light blue shape is the smallest space that is enclosing all of my feasible regions and is still convex. And what it has as a special property is that the optimal solution, if I'm going to optimize over the relaxed space, is going to be the same as optimizing over the original space. So that's great. It's the perfect relaxation. Unfortunately, like in life, we don't always get these wonderful lounge chairs. We sometimes get these horrible institutional chairs, right? And so basically what's going on here is that if I'm not clever enough with these algorithms, and if instead this one is really only taking the very best relaxation with respect to each one of the equations individually, and it's not paying attention to the fact that the equations are somehow related to one another, then the space that's outlined by the dark blue lines is bigger. It's not as good as a relaxation. Now, really, that's even a good relaxation. These sort of institutional uncomfortable chairs become more and more uncomfortable, and now I have this light blue region that's even worse. What's going on and what makes this challenging is that where I used to have the solution at my relaxation coincide with my globally optimal solution, now I have the solution of the relaxation being possibly quite far away from the global solution, which is a problem. OK, so I want to do better. What is the solution? I'm going to relax. And the way that I'm going to think about this is that I'm going to introduce 6 buzzwords. It wouldn't be an academic talk if I wasn't doing buzzwords, right? So these are my buzzwords. And what I will try to do for each of these 6 is that I want to introduce what is sort of important from both a life and a research point of view. So basically trying to argue how life and research go together. So my first buzzword is structure detection. And by that, I basically mean insider information. And in life, when I think of insider information, think of the role of a departmental operations manager at Imperial. So as we all know, this is the most important person in the department. I know you know that too, Michael. And I happen to have an amazing departmental operations manager. This is Anne O'Neill. So one of the things that happened to me when I was early here at Imperial is that the immigration team told me, you can't travel. We think you would be in violation of your visa if you traveled. This is 2 weeks before my sister was set to get married. And I freaked out. What Anne did is that she took a walk and talked to the immigration team. And they explored what were the rules, what was happening. And at the end of that meeting, I was allowed to go to my sister's wedding. So this is all insider connections, right? An insider connection I could never have had myself, but that I got because of Anne. The other sort of examples of insider connections, so the head that was stupid enough to hire me was Susan Eisenbach. And what she would do is she would sit in our coffee room from about 10 to 11 a.m. Every morning, and we could go and ask her questions. And that was how I got a lot of my insider information. Thereafter, Daniel and now Michael, one of the things that they have done for me is that they've put me on really nice committee assignments that sort of show me the way that Imperial is linked up. I really, really appreciate that. So I want what I have in real life in algorithms. Basically, I want these really nice connections. So this is the work that got me hired by this department. I did it in collaboration with my PhD supervisor, Chris Flutis. And basically what we were doing is we were doing what we called structure detection in process networks. So in an optimization problem, you ultimately have to write down a set of equations. And one of the things that we found that was quite common was that people would sort of write down these mixer units, say all of these streams going into one unit, and then they would write down some sort of processing unit, and then they would write down some sort of splitter unit. What we noticed was basically, well, you have a lot of variables that are sort of like x is equal to y, this kind of stuff, and I can sort of eliminate variables. And then we noticed that we had these things where you'd have one variable times a summation, and you could sort of disaggregate and get the multiplication inside of that sum. Okay, so that's nice to have. In particular, what we were able to find when we did that is that you had these linear equations times variables. You could multiply them together. You still have this equation is still going to be true. But what's wonderful about this is that it actually tightened the relaxation. Adding these equations, which were redundant in the original problem formulation, tightened the relaxation. This was already known, but what we did was that we actually found ways of getting these equations. Then you would optimize the problem that you wanted to optimize and return the answer to the user with respect to the original user-defined problem. So this won best paper in the Journal of Global Optimization and got me this job. Okay. So then another important thing that you have to do in optimization is it's really nice to be able to find convexity or even convex substructures. With this, what the equivalent in life is that you're looking for interconnections. And an example of where this has been for me has been the Imperial Enterprise team. And in particular, Rebecca, Becky, and Fiona, what they did for the first couple of years that I was in the Department of Computing is every time a company came, they would put me up and have me present to the company. And after a while, the company representative just got tired of only meeting Ruth. And we're like, okay, we'll fund her. It's just, please, let us meet somebody that's not Ruth. So it's always, I always hear I'm good at attracting industrial funding. They decided I was going to be good at attracting industrial funding. After that, Francesca and Viraj have taken over and are also absolutely amazing in making sure that this happens. So these kind of interconnections, they allow you to basically connect from one dimension to another, from one variable to another. This is work that was done by Mitten Mystery when he was an MEng student. He was the first MEng student that I ever got to work with in this department, and sort of that's where I learned how good the MEng students could be. So he took this really ugly-looking equation. It's unimportant, except that it's quite important in heat recovery, and it has 2 dimensions in it, and it looks ugly. And what he noticed was that if you take this equation and you plot it out, well, it actually looks like its own relaxation already. It looks like its own armchair. And so what we ought to do is we ought to find these sort of structures that exist in optimization problems, and we ought to basically let these structures be their own relaxations, because we have something that's convex. Specifically, what Mitten did is that he observed that, well, in these particular types of optimization problems, mostly everything else is linear. And so he said, actually, I don't want, even though it's its own kind of comfy armchair, I don't even want something that's nonlinear. I want to approximate this with a set of lines. And then he did these set of lines so that he was always below the curve. So basically what happened, when he would solve the optimization problem, he would get an answer that was infeasible. He would add, he would say, well, this would be the point that would be feasible, and he would add a new constraint. Good. Okay, so the next sort of big idea I want to mention is branching decisions. And when we make branching decisions in optimization, basically what we're doing is we're exploring possibilities. And we know that if you can explore possibilities very, very quickly, you're going to maybe be willing to explore tons of possibilities. If it's going to take you a long time to explore the different possibilities, maybe you want to be a little bit more parsimonious with your wish or your ability to explore lots of things. Here at Imperial, the people who help me explore possibilities are the finance teams and the pre-award teams. I think there are not many people in this room who ask more stupid questions to their finance and pre-award teams than I do. You know, basically, can I do this? Can I do that? Is this within the grant rules? Blah, 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 right? And what they are doing for me is that they are basically helping me explore possibilities, but in a way that isn't sort of completely insane all of the time. Okay, I have pictures of Nick Leach and Hassan Patel here. They are the finance team in my own department. And then the Central College finance team isn't, they don't have their pictures online, but it's in particular, Antonia sort of does a large amount of putting up with me. So where I have seen this in tech is in the ideas of Dimitris Letzios, who was a postdoctoral associate at the time. And what he said was, well, let's say I have a setting where I have a planning phase. I can do anything I want. I can take as much computation as I want in the planning phase. Then I have a disturbance phase where everything goes wrong, because we know everything always goes wrong. And then I need to make a set of recovery choices relatively quickly. So I need to really quickly recover. My plots are showing nothing. I just realized that, so you just have to believe me. But basically, what was happening is that on the left-hand side, what was happening was that if he was only going to recover feasibility, so no branching decisions at all, he was able to show that his work in advance, if only he would solve a really good optimization problem, in his case, lexicographic optimization problem, that he would really, if he worked really hard, he would be able to recover after the disturbance in a good sort of way. Then what he showed is that if he would allow himself a few branching decisions, and he was showing both of these things theoretically as well, using arguments from relaxations, if he was going to sort of make a few branching decisions as well, then what would happen is that he could have done a worse job in the planning phase when he was going to then do the recovery. This does sound like how I treat the finance team as well, because I'm always after the fact being like, can I use the money differently than I thought in the grant? Jeremy Bradley, who used to work at this department and then was at Royal Mail, was kind enough to take a look at this work and say, well, that's actually quite similar to something we've seen at Royal Mail, where basically in advance we try to decide how the vans are going to go and how the drivers are going to get assigned to the vans. Then in the morning, all of the vans are broken and all the drivers are sick and all these sorts of things. And when you do the recovery, it turns out you have the exact same properties as Dimitris found in his work. The master's student, Natasha Page, was runner-up for a national award from the Operations Research Society, which was quite fun. Okay. Another thing that is important in this is we think about supporting decision-making. So where I get the most support from the team here at Imperial is via the support teams, especially the research support teams. I've just illustrated the people in my department. There's obviously a lot more than this. So Lucy Attis did all the work for this particular event, so you've talked to her, and then there's a lot of amazing people in my department. What this support ends up being similar to is in the way that a really great support administrator will really sort of scaffold you and make it possible to make decisions. We were looking at sort of figuring out what are the variable bounds for optimizing over neural networks. So just to make sure that I do the problem setting, because the problem setting is a bit different. Imagine I've got a neural network, I have inputs, I have a very simple neural network here, this is just feed forward and fully dense, and then I have my outputs. This is a typical way to use a neural network. The way that Alessio and his team, and these are two postdoctoral associates who were working with Alessio at the time, the way that Alessio and his team introduced me to this problem is maybe I don't want to solve the forward problem all the time where I set the x's and I figure out the y's. Maybe I want to set the y's and figure out the x's. And I can pose this as an optimization problem. What Jan Cronquist, who was a research fellow I was collaborating at the time, said is, okay, fine. It's already known that if I have a fully dense feed-forward network, so I mean there's some ifs here, but if I have a fully dense feed-forward network, then what I can do is I can just extract one node out, and then I'm going to develop my mathematics on this one node, and then I'm going to sort of tessellate for the rest of the neural network. So you have these inputs, you have an output, and I want to figure out, based on the input values of x, how big or how small the output can be. In other words, how big or how small these x's can be is going to influence how big or how small that W transpose x plus b can be. And if I know how big or how small that W transpose x can be, then I can make further inferences on this particular network, which is useful. So he did that. We collaborated with Alessio's team. And then Jan had another idea, and he said, well, that was figuring out, putting all the x's together and saying how big and how small they can be. What if instead I break things up and I partition the x's? And so I'm going to figure out how big or how small the W transpose x plus b can be for each one of these three little input partitions. And what was great about this and what he did is that he was able to show that he was able to get these tighter variable bounds, which was brilliant. So he won best paper in a conference that we have. Okay, so primal heuristics, best observed solutions. When I think about best observed solutions at Imperial, I think about my female academic colleagues here at Imperial. So I've illustrated quite a number of professors and other academics, mainly from the Department of Computing, but also some of the other people I've gotten to collaborate with. A thing to know, whenever you see sort of women in engineering, I don't know, signage, it's always a bit insipid. This is not insipid. This is, and how these people are, is roughly along the lines of, be better, you have to be as good as we are, because otherwise you're a letdown. And they are very, very intense, and they make me be better a lot. So these are my best observed solutions. So I can specifically explain to you how this works algorithmically. Let's say that what I have to do is I have to decide how I'm going to spend my time, right? And then there's going to be some sort of output of my own productivity, right? Now, I'm in my own little field, I do my own little thing, but I know how to observe the global solution in other domains, right? So for instance, let's take the field of computational argumentation. This is in computer science and also in AI, and it has a known optimal solution, and her name is Francesca Toni. Now, let's say I was going to move to the intersection between biomedical engineering and materials science. This intersection also has a known globally optimal solution, and her name is Molly Stevens. And then, let's say I was going to look at optimizing molecular systems. This particular subfield also has a known globally optimal solution, and her name is Claire Agyeman. So these are just sort of three examples, but basically, I can't decide how to spend my time by copying any one of them, but I can kind of look to neighboring domains and try to figure out how they spend their time. So this is basically the idea of Ruby Sedgwick. She's on the AI for Health CDT. Her bio-supervisor is Molly Stevens. I just haven't been brave enough to say to Molly's face before that it's the how to be like Molly Stevens problem. The AI lead for this particular subproblem is Mark van der Wilk. I'm using this particular sub-story not because I led it, but because it fits my story. So basically what's going on is that this is the field of transfer learning where I know sort of what's happening in one domain and I want to figure out what I should do in the other domain. And in particular, what Ruby is interested in doing is that she's interested in designing DNA. She has these different targets and she has to design competitors, and what she does is she uses information that she has gathered from other experiments for other targets to figure out what to do. Okay. Another thing that is sort of maybe my last buzzword is in formulations. So one of the important things that influences whether or not I have a good relaxation is that whether or not I have done a reasonable job of writing down the optimization problem in a good kind of way. That is, I want to sharpen the argument. And sort of where at Imperial I have to most work on sharpening my argument is when I'm working on grant writing and interview prep. It's something that we do really well at Imperial is, or rather, a lot of people have done very well for me, is reading each other's grants, telling each other where we're weak, and really trying to improve things. These are the people who I could remember at the time I was making the slide, helped me with my grants, but I'm sure it's much, much more than that. In tech, what's happening, and an example of where we've had to think about formulations is an optimization over regression trees. This is the exact same problem as I was introducing earlier with the neural networks, but this time, instead of having our inverse problem over neural networks, we're going to have our inverse problem over regression trees. And what Mystery did, he comes up again, was that he developed a really nice way of developing a set of optimization constraints over neural networks. The reason my slide is exploding with people is then what happened is that a lot of people got excited about Mitten's work. And first, Alex Tebelt, who is a PhD student, together with the BSF collaborators, developed this black box optimization tool, Entmoot, which is now in use at the chemicals company BSF for design of experiments. Then we decided that wasn't enough, and so we developed this fairly generic tool, Omelette, we think we're very funny, that takes either regression trees or neural networks and basically translates into Pyomo code. Pyomo is a language for writing down optimization problems. So the reason that there are so many people here is that, one, we tried to make this real at BSF, and two, we tried to make this real with respect to doing reasonable software engineering. And so for that, just this past year, we won Coinaware Cup as the best operations research software that's open source for last year, which is kind of cool. And we're doing 20,000 downloads a month and have been for the last year, so that's pretty cool. Okay, So I've thrown tons and tons of buzzwords at you, and of course, that's what I do. It's an academic lecture, right? But I guess what I want is I want a big picture. And from the mathematics perspective, the big picture is that you're doing all of these things to get a good relaxation. You're then doing a good relaxation to be able to get the globally optimal solution. That's great. But somehow this isn't quite what I want. What I think I'd like to have as my explanation for why I care about all these things, beyond just the mathematical one, is that I am not the kind of academic who wishes to live in an ivory tower. I am the kind of academic who wishes to work at a sort of messy and complicated place like this. And what I'm saying is that ultimately what I am most interested in is computational optimization problems that are very complex and very heterogeneous. If anybody needs just a convergence proof or something to just work because you're going to use one of those components that I presented, probably you got to find somebody else because it's boring and I'm not interested. What I like, and my 3-year-old seems to have been pulled out of the lecture theater for being too loud. But what I like is equivalent to what parents are told to do these days, which is to do messy play. So parents are told to let the kids get very muddy. And so basically what you can think about what I do is messy play with optimization, and that's when I'm happy. Where I get that at Imperial is basically through my collaborations. So PhD student Johannes Weber worked extensively with the geothermal drilling team at Schlumberger. And basically what's happening is as you're drilling, you have uncertainty, and then you have more uncertainty, and then you have more uncertainty, and more uncertainty, and you have to keep making decisions even though the uncertainty is kind of building on itself. And he did a lot of cool stuff there. PhD student Jose Fulch, he has this really neat problem from the chemicals company BASF, where basically as you're flowing down this microreactor, you end up having experiment after experiment after experiment that's embedded inside of this microreactor, but they're coupled with one another. And so he's done a lot of cool exploration in that area. With collaborators at Eli Lilly, and then with PhD student James Odgers, and Krisha Kapatu is a postdoctoral associate, we've been looking at really cool problems in chemometrics. I haven't just gotten the opportunity to do messy play with optimization in research. Thanks to David Brown and the exec ed team, I've also gotten to do messy play with optimization, but now in the teaching way. And David was kind enough to come, so if you want to bug him with your messy play, that he's the perfect person to ask. Okay. The BASF collaborators I've worked with are many. At this point, my earliest collaborators have now retired, so I guess I'm starting to have been collaborating with them for some time. I collaborate with quite a number of people from Sandias National Laboratories in the area of open source software. Worked with Schlumberger. We don't have a current project, but with Anesh Cecilio. And then I get to have a current project that's really quite a lot of fun with Eli Lilly and Sal Garcia. I've also had smaller projects with IBM and Bayer. So I called my title Just Relax. And I keep saying sort of research in life and research in life and research in life. And I guess this is where it breaks down, because all of you know me, and all of you know that if there's one thing I'm really not able to do, it's relax. And so that's, I guess, where this sort of stuff breaks, my ability to relax isn't really there. But at least we've done it in research a whole bunch. So these are my parents and my siblings, and there's an awful lot of math in our family. There's an awful lot of science in our family, and there's an awful lot of love in our family. And then this is my partner, who's now stepped out of the room because the little boy started complaining about something or other. But this is Professor Andrew McPherson. He's actually now in the School of Design Engineering. Oh, he's coming in. You're fine. So he's now in the School of Design Engineering as a chair in Design Engineering and Music. We met in 2003 as MIT undergraduates, and we've never actually collaborated on paper, but we've co-written basically everything. So we ghostwrite grants. You all will find this out soon, but he's really good, and his ace in the hole is grant rebuttals. He got me out of 346 going into a fellowship proposal, and I got the grant. No, he's not bad. He's quite good. The key is disappointment. You're disappointed that the reviewer didn't understand. Anyway, he's very good. And then we've shadow supervised everybody and then navigated life together. As you might imagine, it's not always fun to be a son to the two of us. And so when we are sort of seated together and just sort of get distracted and start talking about work, what our little guy will say to us is, "Stop talking!" And so I think I ought to now follow my son's advice and stop talking, since it's time to relax.
Thank you so much, Ruth. On behalf of the entire audience, also online, this was a wonderful, high-octane, yet relaxing address. So thank you so much for that. Could I just ask your permission to partially open the windows? Would that be all right? Because I think there have been some requests about that. Wonderful. All right. Drop that thought. So we'll just go to the Q&A directly. We'll alternate between in-room and online questions. Maybe we'll start in the room. Any questions in the room? Over there? Thank you. Just wait for the microphone to come. Sorry.
Thank you so much, Ruth. This was absolutely fantastic at all levels, and I personally share absolutely every value that you've brought forward. It seems you've already accomplished a huge amount. So what is the next challenge for you? What would you like to accomplish next?
That's a great question. I feel like maybe I've only gotten started. There are some answers here, but there's an awful lot more to do. And in particular, maybe I've gotten to do some work in the last few years that is now including these data-driven constraints and sort of including a lot of sort of learning constraints from data and also incorporating uncertainty. And those have kind of been a little bit separate in my career, and I would like them to be a little bit more together. Thank you.
Thank you. We have no question online? Any other questions in the room?
Hi, Ruth. Great talk and great, obviously fantastic work. Could you just give us an idea about how hard some of these problems are in terms of non-convexity and how each of those building blocks you talked about may reduce the difficulty of the problem, but also in terms of what is the approximations you're making and how well are you really solving those non-convex optimizations?
Yeah, so it kind of depends on the domain. It kind of depends on the domain. Every once in a while, there's something like what Mitten found where, oh, hey, if this is actually convex and we've been treating it as not being convex, and that would be awesome to do so. But these are problems where, depending on the domain, I might be looking at thousands of variables, I might be looking at hundreds of variables, and we always need to be able to get much better than that. Then you end up with, you just always want bigger. I'm sorry, there was another part of your question. I've now forgotten it.
I mean, can you assume local linearity? Are you given
Yeah.
linearities and local simplifications that
Yeah.
global scale makes difference?
So, I mean, one of the things, and Shicheng, who's a current PhD student, is doing an amazing job of this, is you sometimes want to see how far you can get mathematically before we start making approximations. Where maybe I want to see how well can I do things using all of these tricks before now I'm like, okay, that's as far as I can go, and now I'm going to start in on these approximations. It's very problem dependent.
Thanks a lot, Ruth, for the nice talk, very informative and very entertaining, and thanks for your kind words. I have a bit of a fun question. Are you not afraid at all that generative AI may make you redundant and make you relax completely?
Generative AI. Generative AI will do, I mean, I don't know. It's a good question. Probably not.
Probably not.
I just don't understand. I mean, I don't understand it well enough to know if that any of this work how it would morph or change yet. We're starting to think about it, but I don't have any ideas at this point, really.
Thank you.
Is that an online question? Yeah, thanks.
So we have one question from the online audience. Is like, thank you, Ruth, great talk. You mentioned, you mentioned Eli Lilly as collaboration partner. Do you see particular applications in the occurring of diseases? Is it too difficult when dealing with biology?
Okay. So there's a couple questions
repeat
there.
the questions?
Yeah,
I'm
sure.
not
So basically, one with collaborating with Eli Lilly, and wanted to talk about curing diseases, and then wanted to talk about biology. So a few different answers then. With Eli Lilly, the team that I get to work with is in manufacturing. And sort of making sure that you're doing the manufacturing correctly. I have not seen at this point how the kind of mathematics that I do could sort of design the drugs, but perhaps that's just I'm not imaginative enough. The project with Ruby Sedgwick with the bioengineering, one of the reasons that is such a challenging project, and she has to be a very strong PhD student to be doing this project, is that the data is much messier than we typically see with some of the nice engineering problems that we set up in manufacturing or something like this. So she has to wrestle with her data in a really deep kind of way.
Maybe two more questions, maybe. I think it was back there was the first one, and then over there.
Hi, Ruth. Nice talk. I think you've sort of cracked one of the hardest problems as an academic, which is to be able to both do fundamental mathematics and work with industry. What is your sort of solution to working with industry and being able to maintain this kind of working life? Yeah.
The solution is actually sitting exactly in front of you, and so you can ask her afterwards. Her name is Vanessa Isles, and it's basically you work with CDTs, and then the companies think, oh, I'm just putting a little bit of money, and then they sort of don't chase me as much. So I get really cool problems from industry, but I don't turn the business model.
I think there was one back there and then one over there, and then we probably have to go to the next item. Yeah, I mean, in either order, so whatever is. Thank you.
Very, very, very interesting talk. Thank you so much. You've worked in industrial applications, and perhaps you can tell us one that where the magnitude of the improvement surprised you.
Magnitude of the improvement surprised me. That is a good question. Speechless. I think I'm going to cheat and make it a non-industrial one, but the one where, because the problem with industrial problems and then magnitude of improvement is that the secret is that all of my industrial collaborators are extraordinary, and they've already basically done all of the huge amount of thinking. And so basically a challenge is that then if I'm actually working on a real industrial problem, we can do stuff and we can do cool stuff, but really jumping forward doesn't happen so much because they have done a ton of thinking. Where we were able to jump forward on a more academic problem was in where Mitten figured out the convexity of this one structure, and basically then it was that these problems that had been super difficult were now quite easy.
Claire?
Thanks, Ruth, for the great talk. So you said that you were hired because of your PhD work, but I'm sure you were also hired because of the vision you put forward. And I wonder if you think that vision has changed over the last few years, and if so, in what way has it changed the most, or what has changed it?
Basically, I'm a person who chooses my vision in some part by my pub buddies. So basically, anyone who wants to come to the pub with me, we will end up writing a paper together after some amount of time. This is, what I've presented here is a bit more it's very core to my research, but what I missed a bit of was quite a lot of investigations into uncertainty, and then quite a lot of investigations into data-driven constraints that basically came from being in a computer science department and being introduced to some of this stuff. And then things like getting to work with computational argumentation with Francesca, these kind of things come from just being in a department full of really cool researchers. So in some ways, very opportunistic.
Thanks very much. I think this concludes the Q&A part, and we now come to the vote of thanks, which is kindly given by Professor Stratos Pistokopoulos. Please.
Thank you, and good afternoon, everybody. What a lecture, Ruth. I'll start with inside information and, getting interconnections. We are in the business of getting interconnected. So I'll tell you how I first met Ruth back when she was doing her PhD studies at Princeton with the late, great Professor Chris Fludas. It was 2009, I believe, when I visited Princeton, and she introduced me, immediately she wanted to show me his lab. Those of you who have met Chris, you know how, enthusiastic about this. He took me to the, to the floor upstairs, and then he introduced me to his next big thing, who had the name by Ruth Misener. I said, okay, good. And then we have, of course, I have been observing Ruth over the years. And then it was around summer of 2000, towards 11, towards the end of 2011, I get a phone call from Chris. It was early, late afternoon here, early in the morning in the US. I said, why he's calling me so early there? I said, I have some breaking news. What is this? The couple has been deciding to move to, to the UK, and they are thinking about postdoctoral studies here. I said, we'll make this happen. So I was very fortunate enough to lure Ruth to come to Imperial College. At that time, at the great Center for Process Systems Engineering, the Sargent Center now, and the rest is history, as we have seen. So yes, inside information and getting interconnected, creating this helps a lot. What a lecture, Ruth. The great talent, how you can tell and distinguish a great talent. We have, a room of many talented people, but isn't it the definition of great talent, a person we can elaborate, present things of that level of complexity in such a way that everybody can associate with this and really take, get as distill in a way, the complex and present it with some type of magic projection to make it look simple. Yet, and I can assure you, behind all these kind of concepts that Ruth so elegantly presented to us, there is a lot of heavy work, a lot of basic understanding of very complex things, which are, yes, heterogeneous, but they were presented in a very homogeneous and a very simple way. And that's, ladies and gentlemen, what constitutes a great mind that differentiates the very few, the proud, as they say. The other thing about Ruth is, this, and we talked a little bit, there were some questions about industrial relevance, for industry to appreciate the value that you've got to go beyond the obvious. And by the way, everyone who has done any industrial project can testify they can always improve what they have got from industry. There is no way they cannot improve. So there is no doubt about this. But going for the best absolute way forward, that's a key challenge. And I think, for Ruth to be involved and clearly demonstrating that everything she does can have industrial relevance is great to listen to. The other thing, of course, is pushing the boundaries of the state of the art. And then I think clearly we have seen that in very few years, 8, 9 years now, And I'll tell you another thing. We're not very happy that, Ruth was hijacked by the Department of Computing. We wanted her to stay within the chemical engineering department, but anyway, so we'll pass this. But nevertheless, so she has been pushing the state of the art in problems which many of us, which consider ourselves, at a glance, and then we, of course, pass that we are equally talented, we cannot even start thinking about this, and not only this, and transform those into software tools that people can start using and testing the boundaries of science. So she combines, if you wish, the science with the art, because posing the right questions to difficult problems and extract solutions out of this is not only science, it requires an element of art. And that is ingenuity. And that, ladies and gentlemen, is ingenuity. So with all of this, let me take the opportunity, and I hope you can all join me in thanking Professor Ruth Misener for, being who she is, and for an outstanding lecture, and most importantly, for her outstanding contributions to the science of computational optimization. Thank you, Ruth.
Thank you very much, Stratos, for this kind vote of thanks, for bringing Ruth to Imperial, and for the grace with which you take the fact that she joined computing. Thank you so much. Yeah. I wanted to thank you all also online for having joined this great lecture. I just wanted to say that if you go outside and sort of swerve to the left, there will be a concourse where there will be some nice drinks and a little bit of canapes waiting for you. So I hope to see you all there. Thank you very much, and have a lovely evening.